Today is, and it's Kentucky Derby too, right? Isn't it? It's like one of, yeah. My friends in San Francisco are already drinking. Okay, so yeah, today is very much applied machine learning. There's a lot of material on the algorithm side and the training side, and we don't want to recover all that stuff. There's much more going on in machine learning these days, and frameworks like TensorFlow, which is one that we're obviously going to focus on quite a bit today, and there's another one called MXNet, and these are very production first type of frameworks. The first time we actually kind of saw this was with Spark. So let me go to my intro slide here. For some reason, my intro slide is not the second slide. So my name is Chris Fregley. I run this meetup. I think some of you actually found this Saturday session because of this meetup. I was posting there. I was going to be in town. My little sister lives here, and she lives in DC. So I have to text my mom. My mom was who you guys ran into downstairs. And so I come out here quite a bit, and when I'm here, I like to either do a meetup or hang out with you, meet people and transfer knowledge, that kind of stuff. This is a paid event because of the GPU, and this space costs money, unfortunately. So.
Did you run this? Is Nathan Salmon part of this too? Does his name ring a bell? I thought he was co-host this meetup.
Yeah. I don't think so. Yeah, maybe. I don't know who it is, so that would be weird. The Global Meetup is based in San Francisco. That's really the hub, but we have about 15 chapters throughout the world. And the cool thing, we actually just beat Spark, or the Databricks folks, that was my old company. They do a marketing event every month that they happen to call a meetup. They just did one too. I think it was Azure. It was at Microsoft. I contacted my friend to speak, and they said no, because Microsoft already had a bunch of speakers and Databricks had a bunch of speakers. So I was like, okay, and I will, yeah, because I've spoken at that meetup a bunch of times, but it's a marketing event now. So first time we saw kind of machine learning in the context of production was with Spark, right? So Spark has Spark ML, and the machine learning part of Spark. When I was working there, and I'm still part of the Spark community, of course, people always got upset. Why aren't you accepting our this custom machine learning algorithm or this particular thing or whatever? The reason is because a lot of those algorithms were not parallelizable and not taking advantage of Spark's power. So they've since lifted that. They realized a lot of people want to use Spark with Scikit-Learn, with traditional machine learning, and why limit them? Why not just support it? So one big transition. Oh, and so the thinking there is that while these algorithms are good in the lab or maybe very good in your domain, they don't really generalize very well. So it's the first time, and Databricks created I think it's called Spark-packages or something. It was this weird Maven-like thing where you could post jars with your and tie it to a GitHub thing. It was totally weird. The shady thing is part of that support for that proprietary repo ended up in the open source. So you could do -- projects and you could reference something over there, but it didn't support other people. So they were always riding the line of Apache danger zone. Yeah, who here uses Databricks? Seems like a lot of people do. Yeah. 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 Right. So Databricks is very famous. This is public for kind of slipping in about a month before the official Spark releases. I think they first did it in 1.4 or 1.5, where they and I even felt this was shady. I was a field engineer working with customers, and I had to tell customers that, hey, you have early access to the Apache release that hasn't yet been released, right? Officially through the Apache process. And Cloudera found out about this and actually kind of called out Databricks to say, hey, you can't call this the official Spark or a pre-release. It's not really a release. It's your version. It was a sign of them having total control over the Spark ecosystem, and it was a very bad thing. So they actually had they renamed it, I think it's like the Databricks runtime, and now they can get away with sort of pre-releasing. And Databricks is also doing a lot of proprietary things as well too, right, where they're building custom connectors for S3 and all that kind of stuff. I'm going to tell a lot of gossipy stories because I like gossip. So I watched The Bachelor. And I'm going to tell you fun stories from like Netflix as well too. I don't really have a lot of fun stories from Databricks. That was pretty much a very horrible place to work, like overall. They've gotten a lot better apparently now that they can spread across many people. Before it was 30 people, and we got the brunt of all of the 7 founders every single day. But now they kind of spread out that weird culture, and there's more people in between the founders and them. That's the best way to describe it. Okay. But yeah, we're also #1 Apache Spark meetup, #1 Kubernetes meetup in the world, and #1 TensorFlow meetup in the world. So pretty excited about that. We got about 10,000 people just in San Francisco alone. I think here it's, I don't know, 2,000, 1,500, something. All of the resources from all the meetups for the last 3 years are on YouTube. You can Google, if you go to pipeline.ai, there's a link for community and has everything. So it's very overwhelming. We cover a lot of ground in that meetup. This used to be the Advanced Spark meetup. That was my reaction to Databricks turning into a marketing and moving away from the community. So when I jumped ship to go to IBM Spark Tech Center, I also started that same month like this sort of concept of like the Advanced Spark meetup, which was really, you know, going in and doing deep dives. And people would come to me at the booth when I'd be working conferences and ask questions about Spark, and really deep questions. People would have stack traces that they would have their laptop and come up to the booth, and I would always be watched by my boss, like, can't spend any time like helping people. You have to sell the product. So I'd be like, sorry, I can't. Yeah, I got in trouble one time for going around the corner to go to the bathroom, and I was working the booth, and I got stopped, and like literally I was telling the person, I can't help you, and my boss like called me out the next day and said, hey, you were spending too much time with somebody. So like, I was just trying to go to the bathroom. Very, very weird place to work, or it was anyway. Okay, that was Boston. So this is, if you fall into this profile here, if you have passions about any of these, you'll find this session to be very good. And I don't really have clear break times or anything. Well, actually I do, in the slides I do, but I usually just completely ignore them. But when you guys are ready for a break, I can usually tell everyone's glazed or checking their phone or whatever. But there's this concept of hyperparameters. You guys know about this?
Yeah.
That term hyperparameter? Do you know the term hyperparameter? Okay. Hyperparameters, so when you're like doing machine learning, you're learning parameters. That's the confusing part. Or weights, right? You're like trying to find, you're trying to create a function with weights filled in that could best estimate, you know, some data set. These hyperparameters are ways that are different parameters.
Could you turn your
Yeah, we got a little echo going. So these hyperparameters are parameters. Yeah, hold up a sec. Un momento. Okay, lo siento. Hello, hello. These hyperparameters are parameters of the model that is trying to learn the real parameters. That's why they're hyperparameters. Maybe metaparameters, but don't call them metaparameters. Call them hyperparameters. And what we're trying to say here is that, you know, there's a complete pipeline, and pipeline is everything from the data ingest, so pulling the data off of S3 or pulling it out of HDFS or pulling it off a file system, pulling it off of Kafka queue, all the like transformations that happen. Some of these transformations are typically joining, you know, that's kind of the classic SQL where you're joining tables and joining data sets or joining streams. But there's also now more complex transformations that was kind of spearheaded, the like terminology was spearheaded by Scikit-Learn from Python, which is, or like transformers in the context of machine learning can also be called feature engineering. So like we're always trying to engineer features that then are the samples that are the data sets that we're learning that the model is trying to fit this model to, right, this function. So when I talk about data ingest, like, yeah, we don't spend a whole lot of time doing, you know, the actual HDFS connectors and stuff. So we're more talking about the transformations to get it in for the learning process. But there's also a step when you've trained the model. That's where most people's pipelines end, right? Is when you train the model, now what do you do with it, right? And so that's where we've been focused on the last year and a half, is like really, how do we productionize these models? Now, certain models actually lend themselves to being put into production, like more so than others. MATLAB, R, all that stuff, yeah, right, like Scikit-Learn even, are not meant to be pushed like behind a REST endpoint or in a web app or something. They often are, but that's not really their intended, you know, place to live. They were meant to, you know, talk to an HDFS bucket, have all the time in the world, and can just do batch jobs. If they die, you just restart them in the morning. And that's how most of, you know, the Spark world operates in current, you know, world. But yeah, today we'll be talking about real-time stuff and continuous training and some strategies for that. How to get models into production safely. So one aspect of my Netflix career that I've brought with me every place is the ability to push code into production safely in like a, you know, shadow mode is what they call it, or some people call it nerf mode. It's, you know, it's out there, it's taking traffic, but it's just kind of pushing the results either to a database or it's just not doing anything with it. We're just making sure that each of those services or those models, those like different variants that have been trained differently or that are using Scikit, one of them is using TensorFlow, one of them's on a GPU, one of them's on a CPU. These are all being pinned against each other and seeing, you know, how do they hold up in production. So our idea of the best model doesn't stop with offline validation, meaning we're not just looking at, really, how did this model do on this historical data, but we want to push it into production and see how is it doing right now on current data, right? Streaming data. So we actually don't consider a model best until it's actually pushed into production. And I have a screenshot. Actually, it's kind of an early screenshot from one of our early wireframes that I think actually better represents our product than the current product because we're still developing it. Yeah, so the ability to compare models safely offline and live in production. Also, if you do want to put multiple models, let's say you have two winners based on, you know, so far they've done well offline batch data, now they're doing well online, but you know what? Yeah, we still want to pin them together. So we'll actually send traffic to both. So we could do 50%, 50%, 60, 40, whatever. And then sort of let, you know, like the numbers and the traffic actually dictate what's better, okay? Yeah, also we can like dynamically shift. I don't have it on this, I think it's on the next slide maybe, but we could actually shift traffic as one model is doing better. We can start to shift. These are called multi-arm bandits typically, and we're gonna exploit any early winners, but we're still gonna kind of let A and, you know, if it's A versus B versus C, A is the current champion, B and C are the two challengers. We're gonna throw traffic at all three. If C is the early winner, we'll start sending more and more to C. And C will either tip over and stop doing well, or it will continue to be the best. So I have some good screenshots. Anyone here dealing with traceability and explainability as machine learning? One of the, yeah.
Yeah, it's a huge problem. I typically, when we work, we tend to have something that's black boxable. Yeah. You know, something that the client, you know, they can see like a pile of photos. You have to classify is it relevant photo, yes or no. And you can use whatever model as long as it goes into a file, you know, 99.9% of the time, that's the right category. And if the client is both comfortable with the input and the right bucket is, they're happy to not understand the model actually. But the second you go towards small decisions that need to be made, that's very important. Then you need statistical inference. You need to be able to, like, you know, theoretically say, this is our confidence intervals. We've addressed divide those two teams?
Cool. Yeah, so this is a huge problem. There's a lot of research. This is actually one of the dangers of neural networks. There's this thing called GDPR. Yeah, what's up? Do you need a power? Yeah, there's something called GDPR, which I always forget the full thing, but it's for privacy. It's kind of the overarching, I guess, entity. And places like Germany, very, very sensitive to their data privacy. Yeah, and coming from Netflix, where we expanded into Germany, we had to, that was my first experience, like, oh, wow, these people are serious about privacy, you know, because like we Americans are like, whatever, you can have our social security number, we got LifeLock or whatever, right? Things that don't actually work. This potentially, because neural networks are difficult to explain, right? The power of these neural networks is that each neuron isn't really the important thing. It's the entire network. It's the connections between all of these nodes. So each node is actually pretty dumb, but when they come together, very, very powerful. So when you can't say this is why we like denied you credit, right? This is a big deal. Or denied you a job based on some bias or something. So it becomes very difficult to explain. So the trend, and actually you could see this in some of Google's, there's something called Tensor Hub, I think that they just released, or TensorFlow Hub. There's something else called Tensor Hub that's not the same, but it's this model, like, think of it like little chunks of models. So it's not just one big gigantic inception network is like the, like common example where this huge network, it's, millions, or not millions, but, well, it's millions of parameters. It's tons of layers and, huge and wide and has all these weird offshoots if you look at it physically. They sort of empirically chose this like network architecture because it does really well on the types of like images that they wanted to classify. And I think it's 1,000 classes is the final result. So you would pass an image in and you would get a Rayleigh distribution across 1,000 of those classes. And so that's a huge network, and that's not very easy to reuse. You have to treat it like a black box. You can't really pull it apart without it losing its power. So there's this new trend, and that's very difficult to explain because, and people had made attempts to sort of show what each neuron is learning, and it might be, like edges and stuff. Yeah.
So in terms of the spectrum, the regressions would be at one end of the interpretability, that somewhere
yeah.
on the lower it's random forest and neural networks. But mostly whoever I've talked to, I said, how do you come up with a good, so it says heuristically, right?
Yeah.
You adjust the weights and you add layers or whatever, maybe play with it. So I know there's some research going on, but in terms of interpretability, like what do we know about neural networks as of now?
Yeah. Anyone have a good answer on that? Yeah, you seem to.
I'm opinionated. So, I mean, if you're really trying to explain to a client, it really depends on what you're doing. If it's something that's not, you could have the wrong prediction, it's not a big deal. You deny someone credit, but it's, they have an opportunity to appeal. That'd be a big issue. In terms of just interpretability, like if you have, 10 million weights, typically the way you attribute something is you take the estimated weight times, some median value of the actual data, multiply them together, sum it up by, larger category. You say, oh, 12% of this goes to this factor. So I mean, that's how it's done in practice. Whether or not, an end user, so it makes a decision, thinks that's a good explanation or not, that's totally different.
Yeah, it's I guess what you're kind of asking for is more on the intuition side of things, right? Like how are people going about this today? So just let me finish my thought here. The ability to present a model in small chunks and sort of ensemble these things together or compose models. Now you kind of have a better chance to be able to say, well, this part fed in, because it's not these tiny little neurons part of a large network, but it's actually kind of sub-models that are now participating. And so you can at least narrow it down to a particular sub-model that was trained on this data, these particular biases, that kind of, or yeah, potential biases. Very complex area.
Can you explain
way to at the theory or aspect of it?
Let's table it for now. It's the most complicated part of machine learning, so yeah, it's definitely something we should revisit. So yeah, let's do it. I don't want to break the flow up just yet, though. Very interesting part, very academic part, actually, as well, too. There's a couple companies that are trying to, and there's a couple open source projects. There's one called Skater. He's a buddy of mine down in LA, actually. He works for datascience.com. I think it's SKATR or something like that. If you search that, GitHub explainability, yeah, Skater. He has a way to do it. He has Python bindings for it now, I believe, and yeah. So one thing I'll mention here about our stuff, about the PipelineAI platform, is that we can trace a single prediction through, right? So we can actually tell you, which models that were part of this ensemble actually fed into this prediction. So, it gets you like a little bit closer. I believe Algorithmia does that as well too, don't they? Yeah, they have an ensemble piece to it. Okay, so key takeaways here are there's hyperparameter tuning is typically talked about offline in the training side. It's actually can be applied to the entire pipeline. And the whole pipeline, the entire pipeline, I mean, including production, including how it's doing, how it's serving models and its sort of runtime characteristics, right? There's also hardware-specific things you can do. So if you know that you're going to be deploying to GPUs, you actually have quite a few options. And like data scientists don't know this because they've never been presented this before. There's a bit of a cultural issue as well too, where this happens everywhere. People try so hard to keep the data scientist from having to deal with any systems level thing, right? Like you were joking that you see code and you're happy, right? I've like literally sat here and had someone tell me, wait a minute, I have to go to the command line. Like this isn't the right, workshop for me, and they would get up and leave because they're a data scientist. They feel that they should never ever have to go to the command line or run anything, and that and it was through Jupyter, so they felt that I was enticing them in, right? Like we were joking about this later, but that they were falsely led to believe it was all going to be Python. And we busted out to do a little CUDA code. Yeah.
Now you can tell them it's Turing avoid.
That what? The
Turing avoid.
huh?
Touring the world.
Oh, my world tour stuff. Oh yeah, yeah. You love that stuff, don't you? That was actually just that was a year ago, I think. Actually, yeah. It was East Coast. Okay, so and our feeling is when I first joined Netflix, for example, I was very shocked that I had access to these Amazon servers and that I could access production. That was very weird to me, especially coming from Chicago tech market, which is all about banks and insurance and all the boring stuff, right? Couldn't get to anything without going through 7 layers of DevOps and managers. So I never even, I was surprised I could even browse the web, right? It was like that bad. Yeah, back in Chicago. So there's things you could do though. If you give a data scientist knobs to turn, they're going to turn them. And if you give them an easy way to turn the knob, push that model out or that variant, it's not just about the model anymore. It's also model plus the runtime, right? If you give them knobs to tune either the model or the runtime, or some of the system parameters, if you can present them in kind of a human readable, data science friendly way. You don't have to talk about CPU registers, GPU cores, and that kind of thing, but you could say, just, kind of like roll it up into a generic, term that we're going to try, even if you say GPU specific optimization, people are like, awesome. Yeah. In fact, I always wanted to know how is my model going to do with the GPU? So give them an easy way to push it out there, safe way to test it in production with shadow mode live, and then they can very easily either prove or disprove. Like a lot of times we actually have people that are dying so badly to try TPUs or to try GPUs, and but they don't even know where to start. They talk to the ops guy and they're like, oh yeah, we got to get a one-off GPU instance, we got to get the CUDA drivers on there, we got to do this, we got to do that. So that's where pipeline comes in. And Yeah, by the way, a lot of Pipeline is open source because it was created in the open source, and you know, the platform is the same runtime that you can get on the open source, but you can now get a whole lot of value by putting into the platform all the, you know, metrics that are being pumped out, all of the stuff I'm going to show you today, all of these sort of auto-generated optimizations. We're also tracking, you know, how well these different variants are doing. We're tracking this for you. So yeah, you'll have intuition. You can look and see that, you know, like version B, which is GPU optimized, you know, is faster, but we'll actually show you the data and then start to make recommendations, right, specific to your guys' domain. This is an area I don't think Algorithmia does right now, but they're just, they probably collect the data, possibly, but I don't think they've actually gotten into, they could, for sure.
Well, they claim to do everything, so I'm not.
Yeah. Yeah. And yeah, so like the ability to actually auto-generate these things is very powerful, and all people want to do is just try it out. And a lot of times their model really doesn't gain that much benefit from GPU. Now there's one little trick there. If you're just naively trying GPU, you're probably not going to, you know, see any speed up. There's more to these GPUs, and there's more knobs that you can turn. Like you could actually, so if you're passing each and every request that comes in, and these are small payload in some cases, right? You know, like 1,000 log lines, something like that. If you pass in small payloads, that's not really going to do well on a GPU because you're making one request. You have to move that data from the CPU, you know, off the network and onto CPU, then onto GPU, then back. What you could do is you could actually batch up a bunch of requests. And so this is a knob you can turn as well too. You could tell that server that's receiving all of these requests from across the world to wait like you know, 5 milliseconds, and then collect all of those requests, pass them all in batch, right? Sort of pseudo batch into that GPU, make one big prediction. But because of the properties of linear algebra, you could actually slice up the result and figure out who it goes back to, if it's, you know, people across the world. So there's a lot of kind of naysayers about GPUs and, you know, things out there, and it's because they really aren't actually taking advantage of the GPU's power. And then, of course, continuous model training. There's a lot of people that talk about this. I feel like people really, the people who are doing it don't think they should be doing it anymore from a business standpoint. Continuous model. One sort of hybrid, so, you know, this is where typically you train the model offline, fit the model, right, with an offline data set, and you move it online, and it sits there and it gets crusty after, you know, a couple weeks. With this continuous model training, right, like data is constantly coming in, or you're learning, you know, that this ad campaign did well, and you're kind of labeling data, you know, maybe 2 weeks after, 4 weeks after, right? You can't really label the data right now because it's not labeled yet. It's new data, it's new users interacting with the system. But after 2 weeks, you can run a Spark job that'll then go and label and say, this was an effective campaign, this you know, particular model, right, like didn't do well. And you can now take that same, right, like newly labeled data and send it back into the pipeline. Okay, so this continuous model training is actually, you put out one model server or 5,000 model servers that all have the same model, and you're then pushing updates and saying every 2 weeks or every hour, every minute, we're pushing new weights. And this is potentially dangerous, right? That's the thing, is you really have to find kind of the sweet spot for your domain and for what you're actually trying to accomplish, the business goal. If you start to pick up local trends, that's not good, right? Because now you think the world is what just happened in, you know, the last hour. Typically, what you're doing is an incremental training. That's you know, it's not like you're forgetting about what you've learned and only looking at the last hour. But you really have to be careful how much you put weight on that last hour versus, you know, 2 years of historical data. So the only thing we can do, and right, like again, this is kind of like Netflix thinking, is we can't solve your problems, but we can make it super fast and super frictionless to solve your problems for you, so that you can solve your problems. Okay, because at Netflix, for example, with just microservices, yeah, I was on the like streaming team and doing a lot of streaming recommendations, that kind of stuff. But like we didn't ever we had kind of whiteboard numbers and back of the envelope capacity planning, but we never trusted them. It was more, we were always wrong. And so by being able to, push out these like canaries, they're called, you can like push it out and see if it tips over, and you're basically always comparing to the previous version, right? You're like always doing relative sort of capacity, right? Like, did this new model, yes, it does it now require twice the RAM, then we have to change the instance type that's actually serving that model, or go back and change the model. So it's kind of interesting. Like, you don't really think about that, but when you come into a fairly old company, right? Like Netflix is, I think, almost 20 years old now. You're basically incrementally adding value. Like, so we were streaming, and we were actually, when I was there, streaming had already been there for 2 years, or the code base had been there. They were trying it out, but yeah, it was already like a 2-year-old code base, and we were always doing sort of incremental, updates. So here's the open source side of it, and you can get really, really far with just the open source. Funny little story about the Bay Area. We actually were talking to the Algorithmia folks, and they were like, "Why don't you just use Algorithmia?" And I was like, "All right," like, you're kind of taking the fun out of this, but yeah, the investors. So we were speaking to, it's not the same investor, but this other high-profile like VC company in the Bay Area, and at the time we had 2,000 stars. Now we're up to, I think, 25, 26, something like that. And this person said, "Okay, you have 2,000 stars. For us, in our experience, we are willing to give you $3 million." So that was interesting. So it was the first time I had heard of someone actually put a dollar amount on these GitHub stars. People talk about them. Oh, this project just hit, 3,000 or 1,000, whatever. He said the next step is 6,000 stars, and that's worth 10 million. On the right is this map thing. I somehow lost the link, but there's this site called Red Dwarf. Search Red Dwarf GitHub, otherwise you get really weird stuff. That's not safe for work. And you could put in any GitHub repo. So you could do Spark, or you could do TensorFlow. And it churns for a little bit, and it fails about half the time because everyone's using it. And they're relying on the GitHub API, which is always limiting. So it's a site that will basically go out and pull down all of the stargazers people have starred, all the forkers, all the watchers of a repo, and tell you like geographically where they're at. And so yeah, I do this periodically because it's kind of interesting. Like, I was doing my world traveling, right, and was down in Australia, and then all of a sudden that part lit up, and that was really nice. Red Dwarf, yeah. I'm
sure it's just a coincidence.
Yeah, yeah, totally. And there's a quick start here. So, again, this is not, we're actually not even going to really get into the pipeline stuff, except for all the research that's kind of led into it. But this is all for you guys to do offline and whatever. But the big thing here, I should set the precedent that one thing we do differently, and people are now starting to do this, and again, this is our Netflix influence for the most part, is we actually, when someone gives us a model or a data scientist uses our tool, when they go to actually deploy that model or to do anything, we actually create a Docker image from that model. And they're choosing the runtime. And then we suggest, right, like different runtimes. We say, well, in your particular environment, we think you should try TensorFlow serving GPU, or this new one by the NVIDIA folks called TensorRT. And so we can actually make recommendations. And so these are essentially hyperparameters that now the data scientist has their systems level things, but we're rolling them up into human terms. Like, hey, there's a new runtime. Do you want to try it? And yes, internally we're pulling in the TensorRT libraries, and we have pre-built like Docker images. We slurp in their model, and there's literally, I'll show you guys here in a bit. There's one line of code that you would implement in Python, and it's the predict method. And that could be as simple or as complex. And I think Algorithmia has something similar, right? There's kind of a hook for that. And we have that like come out of the box. We like have it all set up with like Scikit, certain versions, but you can override it just like this.
We do something internally or similar, and since we piggyback off these deep mode Docker images that are very finely tuned, and then whatever model someone monkeys around with in a fully featured
Jupyter notebook. They say, I like this, and we have a couple of commands. You serialize it, package it alongside one of these packages that's built in. Yeah, so we're up there.
So what we're doing is one model per Docker image.
That's what we do.
Okay,
yeah,
got it.
Exactly.
And this, so that's good, right? Like you guys probably get it.
Yeah,
right?
and then we throw it behind Docker Swarm, right, with a service.
Yeah.
So if you need the load balance, scale that.
Totally, yeah. And we prefer Kubernetes because we have other tools that we use for more advanced stuff on top.
Yeah.
And we have the benefit of kind of the late arriver on this, right? Like we were, actually one thing about Pipeline that I used to tell back in the beginning, but it's been like a while now, but when Docker for Mac and Docker for Windows became big, that's really when I like dropped everything. I dropped IBM and I started with, started Pipeline. It's because like this dream, like Docker used to just be data center stuff, and it was Linux, and it was barely worked on Windows, and it wasn't really accessible to data scientists, and it like wasn't meant to be. But now you could actually very easily hydrate or turn your model into an executable, right? That could sit behind a Kafka stream and pull and make predictions and put the predictions onto another one, or it could sit behind a REST endpoint, take JSON, take CSV, XML, whatever, and then like return the result. And so that was always a weird model because you would have to hook into the CI, the actual enterprise continuous integration, and have Jenkins building the Docker image, and you couldn't do it on your laptop. You physically couldn't do it. Or you would be using like VirtualBox and all that old crap. Yeah. See, I even blocked that from my mind because it was so horrible. But now you could actually the exact same Docker image that you can build with the pipeline like CLI. You can that same image that like has the runtime, has your model, and that then can travel around. And that's what gets committed into not really source. We see a lot of people using Artifactory. And,
as we used to.
Yeah, and Docker Hub's a piece of shit. It's just horrible, especially at scale when you're trying. I mean, even for like a small workshop like this, trying to pull down and because right now there's 30 servers or whatever that are pulling from Docker Hub, and it basically wouldn't finish. So we switched over to, right now we're using the cloud-specific one. So if we're deploying in Amazon, we use ECR, which is Amazon's Docker Hub, basically. Yeah, like they all have them. And it makes a huge difference. These servers are very predictable when they start up now.
So on OpenStack, you use the OpenStack analog of that, or are you using souped-up Docker registry images?
Yeah, it's basically souped-up Docker. Yeah, we should be. But yeah, like that was one of those we didn't really even think about that, exploring it. It was always just a bit of an afterthought, but it like ended up becoming more important, right? Like we always just kind of treated Docker Hub as like, oh, it's just like saving, a file on disk.
Yeah. It's
just when it's really slow file system, that's when you start to notice it, right? Yeah. And so this is probably the number one like mismatch when we go into a new data science shop is, oh, well, I don't really want to like know about Docker. We're like, no, you don't have to. You just use the CLI, it's fine. But then they're like, well, yes, I want to make a change, and I'm like, well, you can make the change in the Docker image, and you could export the Docker image and tar it up, and all, you can do all weird stuff, or just run that damn command again. It'll slurp up a new version. It'll it'll slurp in the new code, that new model, the new weights that you've trained, and now it becomes a new version. And they're like, well, what happens to my other version? And I'm like, it's still running, it's in production, just push out this new one alongside of it. And they're like, well, how do I get to production? That's the other tricky part is when we sort of interview new enterprise customers that we're talking to, because it's pretty rare that you can get access to production, right? Like especially a startup like us. And, but the closer we can get data scientists to production without all of this crazy, red tape and all that, the more valuable our tool becomes. So obviously that is a limiting factor. You can still certainly tie into like Jenkins, and we have all the webhooks and things like that for that. And we typically do have to still go through, but if you can get to logs and get to the metrics, because typically we have to hook into their metric system as well too. Like we have Prometheus, and we have all the normal stuff as well too. We have dashboards, but in pretty much all cases they already have like their own enterprise logging. and then like metrics. And so we're exposing all these logs and these things from these Docker containers, and then it just gets rolled in. But like, yeah, so I'll show you guys here in a bit how to actually use Python decorators to wrap and get timings around different functions, or even within a function, like, yeah, within the predict. So this like Docker image thing, it's a bit janky because, you know, like we have been through the other side of it in stocks, right? When you have mutable, so I'll pose one like concrete thing. When I first joined Netflix, we were making updates to live streaming servers. Mm-hmm. We were pushing new configs. We spun up, you know, 5,000 servers, and if we ever wanted to make a change, we had this broadcast mechanism. And just like any broadcast, you know, 5% won't actually get it. So we're like, oh crap, how do we do this? So then we built a tool that was always scanning to see what version. And if there were any anomalies, we would have to kill those instances. They would get restarted with the new values.
Were you using like managed state with a console? Like what were we using of the?
Yeah, it actually ended up being Asgard.
Asgard.
Yeah, which is like the Netflix kind of cluster thing in the, you know, controller. It's now called Spinnaker. The third generation is called Spinnaker. But like we ended up actually, instead of updating, you know, configs and weights and things like that, and hoping, you know, because there was always going to be this period in time when something didn't have it, so the cluster wasn't in sync. So to get around that, because this started to become very important, especially as we were pushing security fixes, and if some, you know, because our streaming servers were stateless, so anything coming in could end up on any other thing, and if they were, if one server had the like newer version of the cert or whatever, and the, you know, other one didn't get it or something, the user would see weird things even from click to click. Okay. So that's the thinking here, is that you can tie everything together. So if you do commit your model into Git, you could actually use that same Git hash and tag your Docker image, and then you could tie everything together and say, this particular hydrated model, this executable is tied to this version in GitHub. And so this actually helps also with the sort of like dependency hell. You know, in the old days it was DLL hell on Windows. Now it's what version of Scikit, you know, your laptop is going to use something. Because keep in mind, it's really easy to bump up and not know what version that you're on anymore. If you install one thing with Pip Install, that if it has a dependency on some other library, it's going to bump it up. And there's a million ways, you know, there's so many different ways. Using Conda, you can try to control it and pin things. But at like any given point in time, one of the servers that's between your laptop and production is likely not it's not the same version, right, of the library that you depend on. And this matters from performance. One thing also we've discovered recently is the Intel Python distribution, right, like surprisingly, is quite a bit faster in a lot of cases.
MLK?
Yeah, the MKL.
Or yeah,
because Martin Luther King. Yeah, I always like think of it opposite of Martin Luther King. Right? Yeah, so MKL, it's all built in, and of course, so MKL is an optimized linear algebra, you know, library. You can think of it, and it also has, it's taking advantage of newer CPU hardware that can actually do vectorized calculations. It can take in like vectors and not just individual scalars and, you know, multiplying them, but to take in, you know, vectorized. And so that's also something else too, where we would get people to install that Python version like locally, and they're seeing good performance when because with this Docker image, and yeah, I'll show the screenshot here in a sec, you can actually do a load test from your laptop and actually, you know, pound it with like web requests and simulate. Now it's your laptop, so it's not real production numbers, but like keep in mind that you are always like diffing against the version before. So like the assumption is you are only ever going to build a model once, and then you will always be like refining it from that point on. So you would like run it once, get the numbers, push it to production, it's doing fine. You would make a change, you know, either some like training data or some of the hyperparameters. You would then rerun that same load test on the same laptop. The only time that's failed me, where the numbers were wildly different, and I couldn't explain it, was when I was watching a Netflix movie behind the scenes, and it was competing with the hardware. So I was streaming Netflix. This was not at Netflix. This was actually just a few months ago. I was running the load test, and because the load test was using GPU and CPU, and the actual streaming video was actually competing. So I was like, oh crap, I shut down Netflix. So, but that's kind of rare when you're working and watching at the same time. So yeah, you're burning in all of those dependencies, and so there's no question. So something like that, like Intel, it was on my laptop, and then we pushed it to the dev environment at this customer, and we assumed that it had the same. That Python version was the Conda version, or it was a different version. So you wouldn't even know. If you're just moving the model asset without the runtime, it's going to end up in a different runtime, potentially completely different configuration. With this Docker image, you still do have potential hardware differences. If you end up, this happens all the time with the cloud, by the way. Unless you're really careful about the instance type that you're requesting, you could potentially end up on an older Intel CPU. And actually, in TensorFlow's case, like TensorFlow just doesn't work. It'll crash and say, you told me I had access to the newer, Broadwell or the newer Skylake CPUs, right? Because oftentimes people spend so much time on the GPU, but then they pick an instance type that could potentially be a CPU or like a bad CPU. Yeah. So TPU, very specific to like deep learning. Yeah, it stands for Tensor Processing Unit. So yeah, it would be. And the interesting thing is the new GPUs that we're all going to use today actually have Tensor cores on them. And so this was like the NVIDIA's, like, yeah, fine with the TPUs, but we have Tensor cores, and our throughput is 40 times what you're saying. So there's this little like battle going on. So the GPUs themselves, they are very, very high number of cores. They have 5,000 cores, things like that. This latest V100 is the like model name for it. Also has about 700 of these Tensor cores. And so TPUs and Tensor cores are both optimized for the most common, it's like matrix multiply plus a vector add, kind of thing. So very, very optimized for, like the most common thing that you're doing within deep learning, right?
Linear combinations spanning vector spaces.
Totally. Whereas GPUs, sort of like traditional GPUs, have this like a bit of legacy and a bit of technical debt, by having to render textures for, graphics cards and games and, things like that. So, but these Tensor cores are there to address it. And I'm actually going to give you guys a little secret, because with every piece of new hardware, there's always, there's like mechanical sympathy is the term, right, that like people use, which is you kind of have to understand how the chip works. This is like years and years of like chip design, but if you really want to get the best performance, you really have to understand, where are the registers, how far away is the L1 cache, the L2 cache. And one trick with the Tensor cores within the, that like V100 GPU, your matrix, each dimension has to be multiple of 8. If you're off the multiple of 8, you will not activate those Tensor cores. And you'll end up on the older crappy cores, for the texture rendering and be competing there. So yeah, I have a slide on it. And the way that you can get it to those multiples of 8 with your recurrent neural nets and your like convolution neural nets, you're specifying, channel sizes and, all. So like parameters that you choose at our like data science level can actually affect those dimension sizes. And the cool thing about the TPUs, so this is Google TPUs, not the GPUs, is that Google actually has a really slick profiler that will show you as your job is running that you are not on. So I'm mixing, I'm mixing hardware here, but those Tensor cores on that GPU, they want like multiples of 8. On the TPU side, there's some other magic numbers. We haven't figured them out, right? Like Google's actually pretty secretive about like a lot of this stuff. But these TPUs have magic numbers. And really the only way to detect them without knowing the behind the scenes is just empirically, change the sizes of your matrices and figure out. But the cool thing is that you're actually given this profiler with TensorFlow that can tell you if you're on a power of 2, right? Like Google loves powers of 2, right? And it'll show you the dimension sizes and say, here we had the pad, and it'll have, green if you're in the green zone, and it'll be red if you're in the red zone. So it's kind of hinting what, for that specific like Google hardware called TPU, they're actually telling you how you should change your like application level. And that's something Spark never had this, right? Like there's all these little hidden secrets about Spark. I probably know maybe 1/100th of them now. There's been so many since I was there. If you don't know them or they're not documented or you don't hear them at a Spark summit, you just won't know, that Spark is optimized for such and such case. Now Spark actually stays pretty hardware neutral. That actually comes from their VCs as well too, which is very interesting how these VCs can actually influence an entire open source community, where they're really not allowed to spend too much time because their business model is more generic and let's help like every company and let's try to make money from as many people as possible. They're really not allowed, and this is probably going to change, right? The Spark Summit's coming up, I think, in June, and from the rumblings I hear, there's definitely going to be TensorFlow support for sure. It's just a matter of, and like Databricks itself, you can deploy on a GPU, but it's kind of pointless because you're not really using it, unless you're writing your own CUDA code.
Yeah, I don't think the Spark ecosystem wants to be built as only good for ETL, right? They want to stay relevant, like the ML or the AI space.
Yeah.
Yes, going back to talking about like the runtime drift and essentially how Docker solves that.
Mm-hmm.
I haven't really actually used PipelineAI. I imagine there's some sort of notebook interface, some GUI, you're training, and you click like submit model or something.
Mm-hmm.
But you just pip freeze the requirements for whatever that is, and do something and port that into the Docker, along for the Docker file.
Right. It's actually, so when you create a new project, which can either be a function, right? Because it's not just models, it's also the serverless thing, blah, blah, blah. And you can create a Spark job too, which is cool. But all three of them get deployed as functions. And by default, if you select a particular model type, it'll pull in a common profile of, right, yeah. So we're using Conda internally, but you could specify pip, of course, and then just get, but the sort of, I think the kind of higher level question is, can you customize the pip install or the actual requirements?
Yeah. Well, I didn't know if like the data type's in there,
if there was
installing,
like a freezing, got it, yeah.
It imports the OS package or installing stuff.
Yeah.
Through the terminal, and suddenly like, why doesn't this work? Like, I don't know either. And
Yeah, actually, that's a good point. We typically, people have, it's one thing to get them to use Conda, that actually hasn't been a problem.
Yeah.
That's usually like the case already, but they like typically have it already. Either they've frozen. We have a particular like file name convention, and then it just gets picked up and pulled in. But yeah, you could override it and all that too. But yeah, that's kind of a cool, cool feature request. And one quick note on the Spark thing, you would think that they want to stay relevant in the AI world, but and this comes directly from the CEO, is now Ali something. 1% of enterprises actually do AI.
Yeah.
And if you go into a board meeting and say, we're going to spend the next 4 years focusing on 1% of very small market to begin with, it's not going to fly. So this is where you see the ETL is 99%, actually 100% of enterprises do some form of ETL, and so that's where they're at, basically, which sucks. I mean, it was like down to my day-to-day as a field engineer, I would say, yeah, guys, these folks want to do Spark streaming. Can I help them? No, just get their ETL in and then move on to the next customer.
A little, completely relevant to TensorFlow, but coming to the ETL and streaming thing.
Yeah.
Spark is heavily investing in promoting structured streaming, right?
Yeah.
So, even these streams, I don't think is getting
Oh, yeah.
focus and it's completely structured streaming. And they're talking structured streaming and they're also talking machine learning. So do you think they both complement each other, like you need streams?
Yeah.
For machine learning, do you think they are a good combination or no?
Yeah.
So they're focusing on those two, so.
I forgot my mom was down there, probably sitting there. I think everyone's here. Yeah, we kind of touched on that a little bit. I think the streaming, are you talking about predicting off of a stream? Yeah. So that's pretty common. In fact, there's one weird case that we see, right? Like pretty much all data science teams go through this. Or it's more so on like the application side, where they're trying to build a REST endpoint and they're trying to use Kafka. Like all they want to do is use Kafka. And so they build these janky systems. Yeah, have you seen this? These shims where you send in like a request, JSON, there's some layer that puts it onto a Kafka topic, then there's a prediction that's made, it gets put onto a prediction topic, and then that like web request on the Tomcat server or whatever is like looking and waiting for a particular response. And so you're like adding another, like a streaming engine and a distributed streaming cluster and trying to do real-time predictions, but sticking in like a message system. It doesn't really make any sense. But, yeah. But yes, the holy grail is streaming training, where you can train, but yeah, like I was saying before, you don't always want to do that because of business reasons and.
Business reasons aside, like the fact that it's computationally expensive or complicated stuff. One reason, just theoretically, like why you might want to do this is, and you mentioned this a little before, like what we were doing at like essentially, you train models, maybe you have 2 years of history, and you might have this like local spike that is anomalous, that could be biasing your weights. If you have like a good model that really captures in a robust way some sort of data generating process you're trying to capture, if you're streaming, you typically it's exactly what you're talking about. Like if you only have access to the last 60 seconds of predictions, that could be this total, like you could be in some sort of regime of one of multiple regimes, and whatever you just trained is not represented the whole. So at some level, it makes more sense to train the models with richer data that really inform coefficients about the real process, and then you suck that back and just score against the stream.
Yeah, and also too, if you start seeing new data that like one particular sample of the data is coming in all of a sudden, I mean like this is in the, yes.
I have a stupid question.
Yes.
So this Apache Spark is umbrella organization like. Let it be. Your workshop has got both Spark and Kafka.
Yeah.
They may have some parallel functions. So what is Spark being used for? What is Kafka is being used for?
Yeah, and people always want to use them together, right? It's a common configuration. One interesting thing about like Databricks is you tend to notice that those like peripheral projects and Spark tend to match whatever they're like using internally. And then they're like, oh, well, yeah, we have to work on Kafka, 0.10, so let's go build 0.10, or let's start to accept pull requests and pay attention. So said differently, Databricks is going to pay attention to areas that benefit Databricks in the Spark chain, which is common. I mean, Cloudera does this as well too, right? Like everybody does this. So your question about when to use Spark, when to use Kafka, yeah,
How do you use them together effectively?
Yeah. I mean, Spark streaming is the obvious, right? We actually have been talking to more and more people, and this is more people starting projects today that are like, well, I started to design this with Spark. I really just want streaming. Like, why do I need a Spark cluster when I already have a Kafka cluster? Kafka supports Kafka streams. Doesn't really have a good Python API for Kafka streams, but we'll find some open source ones. Yeah.
I think that probably would have supported that.
Yeah.
What I think what happens is if you want to tune performance, instead of using REST, sometimes you push it to
Sure.
RabbitMQ or something, but most of the messaging, if you don't want this validation, then you use Kafka, and then the Kafka messages, you can string them to Spark.
Okay.
Well, you're talking about just like when you're just pushing logs through, and it's like, I don't care.
Yeah, you don't care. Well, you're pushing this like broadcasting, right?
Yeah.
So you
Yeah.
send them, and then if you want to capture some of that data,
Yeah.
I think you can.
Yeah.
And definitely on the data side, like if you actually train a model, you definitely want to have, Kafka, consumer producers that do the validation, the enrichment before you actually do that to the model, because you can train something great, and then if you're getting bad data in, your predictions are like all over the place.
Okay, so we have to get through this section here, so sorry to keep, yeah, we're only on slide 9 of 260. And I think I'm like required by law, by what city, what town are we in, what state? Yeah, Virginia law, to give you guys a break.
You're really, it's a law.
I'm just making that up. Yeah, I don't care anyway, I'm not giving you a break. Yeah, yeah, a bunch of traction. So a lot of these folks were early, they're kind of on the advisory board of the product and helped define the roadmap and blah, blah, blah. Yeah, we install your cluster. We have Community Edition. Oops. Community, of course, we got the enterprise. We just slapped beta on there, gives us a little Google style. Yeah, have you guys heard of these platforms? This is actually similar to what Pipeline, yeah, so our mission is very similar to like Uber Michelangelo. This is a very popular blog post. I'm sure you read it, right? Yeah, you guys read Uber Michelangelo. What's interesting is that the VCs actually know this term or know this blog post. Some of them know the bottom left as well too, the famous paper by Google in 2014 about the high interest credit card technical debt.
Yeah.
And there's this really powerful chart they show that there's a bunch of infrastructure and a tiny bit of machine learning, right? Or in terms of like effort, for these machine learning projects to actually get them deployed. And yes, Uber Michelangelo covers 6 different areas, and this is supposed to be used by all of Uber, although we've been talking recently to the ATG group, which is the advanced technology group within Uber, doing a lot of computer vision, and they're asking a whole lot of questions that I keep saying, why aren't you using your own product for it? And so Uber ATG kind of has the ability now, especially with the old CEO gone, I guess, where that particular business unit can actually do their own thing, and because they're very image, right, like computer vision and yeah, the autonomous driving and that kind of stuff. So so their claim is that Uber Michelangelo is very, very specific to Uber's current like use cases, but isn't very adaptable. And so that's actually one of our challenges, and it's a challenge of like any platform, is how do we have enough hooks into the system to make it valuable to yeah, to lots of different people. But so also interesting, the bottom right, someone sent me this at the end of last year, was there's a job that's available there. Yes, I'm not looking for a job, but there's it's at Netflix, and I was like, why are you sending this to me? And she said, read it. And I was reading, and it's basically Uber Michelangelo, it's how Google, all the papers that they write about productionizing, it's also how, Pipeline is doing things. So it's essentially, there's, 2 or 3 bullet points in there that really highlight it, which is we want to get models into production quickly. And one thing that actually motivated me early on when I first started Pipeline, like beyond just, having Docker. Oh, and by the way, Kubernetes now runs on like local laptops, both Mac and Windows. And that actually propelled us, right? Because we were doing all these hacks before where we had one gigantic Docker image that had all the services, because that is all that would work. In our cluster, it was split out, but we were always having to hack things and, do weird stuff for the local. And now local supports Kubernetes, so we could actually.
Do a Minikube?
No, so it's not. It appears that there's overlap in those projects, because I do see, error, like stack traces and such in that area. But it's literally, if you're on the Docker Edge channel, you can, like, yeah, you have a Mac, just like go down there and you can turn on Kubernetes Yep. And it works for both Mac and Windows. And it's current. I think it's 1.9.6 or something. And yeah, they're up to 110 or whatever on the main line. So like people always say, well, how are you different than Uber? You know, Michelangelo. And I'm like, do you know anybody besides Uber using Michelangelo? Right. And so, and now Netflix is also. Oh, and I didn't finish that thought. My old boss from Netflix, from the streaming team, actually took that job. She had left, joined a couple, you know, crappy startups, and then went back to Netflix like 5 years later. Because I was, yes, I was updating the slide to see if they had changed the description, and that posting was down, and I Googled that title, and it like literally came up with my old boss. Like
LinkedIn profile?
Yeah, yeah, like just started like, I think February or March. Yeah, so we support everything, blah, 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 blah. I'm not gonna bore you guys with this. Inference, the key here is that the folks from NVIDIA, this is from just a couple months ago at the big GPU tech conference in San Jose, they're doubling down on the inference. And this is that TensorRT thing I was saying. So we've been working with this group for over a year, and it finally is now part of TensorFlow. So one kind of general pattern, by the way, is just like with any open source project, at first they want contributions from everybody. Spark did this. I wrote the like Kinesis Spark streaming, and it's very specific to probably Amazon, but they pulled it in. They had Kafka things that they pulled in. They were pulling in, I think right around the time Google started getting involved, they were like, all right, let's hold up. We can't. And the problem here is people flake, right? So they would, and the larger your open source surface area, and if your team stays small, or like the engineering team, you then depend on other people, and other people have jobs and families and that kind of thing. So Spark went the other way. With Spark 2.0, they shed all that stuff. So now all that stuff is in contrib packages or in their janky Spark packages or whatever. And TensorFlow is in that, all-encompassing, we want everything. If you ever want to keep an eye on TensorFlow's build, this is kind of like a random point, but it just popped in my head. If you go to ci.tensorflow.org, that's their public Jenkins server. And I spend quite a bit of time there because we're always, turning flags on for specific customers that have different hardware profiles. And all of a sudden the build will, our build stops working. I'm like, oh crap, they're up to a new version of Bazel, or they've changed, something. If you're building TensorFlow from source, it's like a full-time job for someone outside of Google. But what you can do is go to the nearest one, because Google isn't building all of the different variants. There's hundreds and probably thousands now of different parameters, and then a whole ton of combinations. So they're building ones that are going to help them test the parts that they're focusing on, right? Like Python 3 is always kind of lags behind Python 2 because Google likes Python 2, so there's always Python 3 problems. But you could go there, you could find TensorFlow serving and find one that's close and just compare it to what it was a couple months ago when you looked at it last, and you could see the new parameters. So yeah, so TensorRT now is a sort of 1.5 class citizen. It's in the, it's fairly easy to install. You just specify a little parameter. Of course, you have to be using the Volta V100, which we are today. Okay, I'm gonna skim through these, but the big point here is if you can make optimizations on the prediction side, there's millions, billions of these happening per second. If you make these sort of already well-known optimizations on the training side, there's hundreds of training jobs happening per day or whatever. It's nice if you shave an hour, that's cool, but 1 hour times 100 is way different than 10 milliseconds times. God, I can't do the math that fast, but so there's huge performance optimizations that have yet been explored, right? So I've already described a lot of these where people don't even know that they can make these knobs turn. This is the early kind of wireframe thing that we came up with, being able to see the entire pipeline. And so it's offline training metrics. So those are the, sort of first blue block. And then Pipeline can do auto like optimizations, right? It can say with one checkbox, yes, right? Like I want to do like GPU, for example. That's how algorithm is. But now, like you could also say, I want to try the Intel Python distribution. I want to try to run it on my data center versus Amazon versus Google, right? Like in fact, we have a really cool demo that seems to capture a very specific set of like enterprise customers that are very interested in multi-cloud. It's not hybrid cloud anymore, by the way, according to VCs. It's multi-cloud. So where we could actually shift traffic, so shift if there's model servers, running all on like Azure, and now Google becomes cheaper, because maybe, or if you start with Amazon, you're on spot instances, which are cheaper. And throughout the day, you start to lose the spot instances. We can actually detect that because we're tracking cost per prediction is one metric that we pump out. And it's based on the particular instance type that you have. It's based on, sort of the like surrounding. And so we could actually shift traffic over to the cheaper cloud throughout the day.
What tool are you using to actually, after you build the model runtime, you have it sort of deployed, to go and I have a job that says, okay, this thing's alive now. Let me go hit this, with prediction request or whatever.
Yeah.
Is that like a Kafka streaming thing, or is this like a Jenkins integrated with a Kafka? What's going on?
Yeah, and so do you remember I said one of the challenges of a platform is being flexible enough and so in my head there was stuff like that happening, and then like one of my co-founders was like, well, why don't we just do this serverless thing everyone's talking about? And it was like, ding, ding, ding. Yeah, we can give them a hook to basically do anything.
Yeah, but with that hook, are you using like Jenkins, like
for like the actual scheduling or for the complexity and things? Yeah.
Yeah, you always use Jenkins.
So we're actually right now, those things can't be that, like, we're just now getting Spark jobs to be one of those functions, right? Yeah, because like I said, we treat anything like a function right now. If it's a prediction, if it's a Spark job, and it's a snippet of code, and a bunch of libraries or a bunch of packages that you're specifying. The Jenkins stuff right now is a first-class citizen when you actually go to push the model out. Because that's usually where we're hooking into an enterprise's like existing Jenkins. But yeah, I know what you're saying. And we actually have been prototyping both Airflow as kind of a way to do that, because people seem to like Airflow. We've had some issues with Airflow. That project really just kind of seemed to come to a halt, right? And there's still active development, of course, but all the cool stuff that we were waiting for, people left Airbnb or they got busy with their own startup, and just kind of, it's in.
Startup sounds a lot like Airflow. Okay.
Yeah. And it's like, so the like short answer is yes, right now haven't had enough consensus from people to actually pick one. So it's kind of free form. And as long as we could do like just a simple webhook right now, yeah, people can hook into it. So here we're actually tracking everything. This is kind of a glimpse into the Pipeline Python API, for example, where you're doing these hyperparameters, and you have the observations. I'm going to actually skip into SageMaker and CloudML Engine. We could talk about that break or something. Okay, TensorRT is doing a bunch of cool stuff with your TensorFlow model. TensorFlow Lite's pretty interesting. So they've been really careful recently to not pigeonhole this project into mobile only. In fact, like our mobile phones now are as powerful as some of our like desktops, right? So it's not really mobile that they're targeting here. It's these really tiny devices, right? And the ability to get models. So like typically when you run a TensorFlow prediction, you have to have TensorFlow serving loaded, which usually has to have all of TensorFlow, all the libraries available. If you can upfront trim out all of the unnecessary parts of TensorFlow and the actual underlying operating system, right? So now you can create this C library that can then be linked in to your tiny app that's running out there. That's the bare minimum that's needed to do this prediction, to get from the input to the output. Okay, and so that's where models go from, you know, what would normally be like a 60 megabyte footprint when they have TensorFlow fully loaded, down to like 70K, because it's like literally just going along, you know, pulling in the libraries. So you give this tool your graph for the prediction. You tell it where to start, where to end, and it will literally traverse the graph and pull in just what it needs from TensorFlow.
Like the Alpine of TensorFlow.
Yeah, totally. Yeah, that's a good way to put it. Yes, Alpine is like a super like minimal Docker distribution. TPUs. So I'm going to talk a bit evil about Google here. That might not be very obvious and would probably prevent me from ever getting a job there if I needed one. But I'm going to just kind of state the obvious here, which is whenever you come out with anything that's cloud specific, this is going to raise some flags. And when you have a really, really high profile open source project that is heavily optimized for cloud specific hardware that's only available by one vendor, that's going to raise some eyebrows, right? Google is generally viewed as not evil. I'll let you guys decide. So these like TPUs, one very interesting thing. So it stands for Tensor Processing Unit. They're $650 an hour, which seems a bit high. So obviously the next question is, well, what is the real, you know, is it actually worth like $650? And of course the answer is, well, it depends on the inputs, you know, the data that you're training on. It depends on how well you could actually like utilize that, or like TPU. If it's staying at 1% utilization because you can't feed data to it fast enough, you're going to get crappy results, right? It's not going to be worth it. One thing, there's one other little sneaky thing that these Google folks did that I like discovered the hard way actually preparing for this, was you have to use Google Cloud Storage. It like literally will not let you even train on the VM that you're running within Google, that like local file system. It just says, it like literally, I Googled the error, I think I have a screenshot of it, and it says, yeah, local file system not supported, switch or copy that data into Google Cloud, and then we'll be able to train. Yeah. And how that like manifests itself is the TensorFlow graph that you're building up has a node to pull from the file system to start the training job, right? To like get the data in, and that node, just for whatever reason, is at the bottom of their list to implement on the TPU. Yes, obviously CPU, GPU, the GPU folks, that node to pull data in from that like local file system or from HDFS, that was written by NVIDIA, or rather possibly Google. But each node for each new chip has to be implemented by that chip vendor. And we actually, over the last year, have been working with two companies that have something very similar to TPUs that they're, of course, trying to get into Amazon and into Azure. And all they do right now is keep an eye on TensorFlow and implement any new operators that have shown up. Because these, like, yeah, these deep neural networks, these frameworks have just all these weird edge, you know, type of operations. It's not all just matrix multiply. It's yeah, there's like a lot of, you know, subtleties. So in fact, the next slide here shows, so this is open source, this thing called Tensor Board. And they're like, oh, by the way, while you're in here, like debugging your graph, we're going to show you, you know, like how much faster your like model would be if you ran on our proprietary hardware that only runs in our cloud. This actually specifically is showing you the compatibility. So they're saying for this graph, which right now that number always hovers around like 99% to 100. It's typically the only one left out is the local file system one, because most people have a graph that's pulling from local or from HDFS, and they're like, yeah, we don't. Now, oh, and so this is telling you if you were to convert this model over onto our hardware, we can optimize 92%. There's a couple operators that the TPU doesn't know how to handle, or we've chosen purposely not.
We can't do gradient descent?
This, by the way, is literally from TensorFlow 1.6. This was an older snapshot, so it seems unlikely that that would, yeah, I don't know why. I never caught that, actually. here's that like goofy error. So it's like literally on their like FAQ, and the upper right was the error I got, which is, you know, I was trying these TPUs at boom, boom, and I'm like, oh shit. And it like wasn't a big deal, but it was like one of those things I just didn't want to deal with at like 2 in the morning last night, right? The same profiler, interestingly, that works. So there's this profile tab that shows up when you use TPUs, and it's a plugin to Tensor Board, and you install it. There's a nice clean pip install. It actually installs pretty cleanly. Works better if you're on 2.7 Python than 3, but so yeah, these slides are a bit out of order, but this is actually one of the charts that like you can get from that plugin, and it's not just telling you how the TPU is doing. It's actually telling you that you could be doing better on the actual ingest from like Google Cloud. It's telling you that you actually, you know, have more threads available, for example, that you're, you know, it's like telling you you should be prefetching here, showing prefetch. Actually, this is doing prefetch. I'm just highlighting it. So like prefetch is the ability to sort of buffer up. Because you know, typically when you're training, you're doing you're doing feature engineering, right? And you're like cropping images, or you're changing the background, you're sort of augmenting the data to force that network. You're like blurring out things, right? Like Street View. My buddy worked for like Google Brain's Street View team. Says that they had a set of like labeled training data. The goal was to be able to blur out faces and blur out addresses from those Street Views, when, you know. And the way that they were able to get like really good results is they would go in and change the blur and change the background, and they had one set of data, but they were able to create, you know, 5, 10x the amount of data by each image. They would look and see the bounding box, and then they would do something interesting, and then it was labeled data. So and they would feed that into the network. And so prefetching would actually, you know, if you think of it like a little subgraph within your main graph, it's going to do the feature engineering and queue up a bunch so that you can keep that TPU or GPU, in this case TPU, fully saturated. Okay. I'm going to skip through TensorFlow Lite. Just to give you guys a quick glance, here's the pipeline CLI. We're, you know, creating model here. It's kind of a walkthrough. This is that what like used to be called TF compile, which is now, so yeah, this is really where, you know, pipeline features kick in, which is, yeah, we can deploy your models, you know, yeah, we can train them as well too, that's fine. But there's that step in between, the optimization step, that we really want to highlight and like raise awareness for. And so, yeah, this is a case where this model went from 70 meg down to 70K. And again, you feed in the actual model, which has the graph. That's the third or fourth parameter down there. You tell it the input, which is the node in the graph that's going to take the input for the prediction. The output is the, that's actually a node that has the result of your matrix multiplication. Yeah, this is just linear regression. Okay. Oh, and so here's the predict function. You could do bare bones, just have Python predict, or you could start to add in, yeah, these advanced metrics that'll actually give you really fine-grained timings within your specific request. So this is cool. This is something that we're not aware of anyway that people do. It's the ability to not just compare system metrics for these models when you're running experiments, but actually compare the predictive power of these things in like real time, right? And so because we're kind of a serverless core, you can actually introduce your own ways to like quantify the prediction so that you can chart it on a two-dimensional axis like this. So because we're shadowing traffic, we're sending the same input to all 3, 5, 10 models, and each of those for the same input, which is x-axis, would end up on a different y-axis, which is the prediction. And the way that you would convert that like prediction, which is, you know, some sort of human grackable thing, you can actually put in your own function to then sort of canonicalize it for that. Okay, here's an example of different predictions. So this is the exact same model, but different runtimes. So boom, 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 TensorFlow serving CPU, TensorFlow serving GPU, TensorRT GPU. And this is all three of them. Didn't make a single change to the model, but we're just literally wrapping it. This is the most basic where you're not setting, you know, the request batch size and things like that on the prediction. Yeah.
I know Scikit is similar to Flow, doing supervised learning. TensorFlow, does it unsupervised learning only, or?
Most of, yeah, so all of them do all of them. H2O does supervised, unsupervised. Scikit does unsupervised, and TensorFlow does them all. Yeah, that's the kind of high-level answer. Probably 99% of, if you're just learning TensorFlow, all of the examples will be supervised. It's labeled data. The popular unsupervised, especially in traditional machine learning, would be like k-means clustering, you know, which separate from the k-means part. It's taking data and it's just, there's like nothing telling it what to do. It's just trying to find clusters. And if you tell it there's 10, it'll find 10. And it's just literally doing like Euclidean distance between those things. The other popular unsupervised is called Auto-Encoders. And that's where you have like a bunch of images, for example. You squeeze them into a smaller like mathematical representation. And then you unpack it and use that same data as the label. And you like do this over and over until you kind of, if you think of like a cheese strainer or with a cheesecloth or whatever, where it's like, you know, some stuff's coming through, that final thing is the learned like representation of that input.
Kind of, if you're asking a question kind of about the motivation, why would I choose Scikit-Learn versus TensorFlow?
Yeah.
That's really one of TensorFlow is built to use a distributed computation, right? It's built upon this like out of the box notion of going across, you know, data across different machines, doing there, and stuff like that. Whereas Scikit-Learn is single machine Python. And so the motivation is really just, can I run this at scale? At scale nicely.
So TensorFlow is only for neural networks, right?
Oh no, you can do anything. Yeah, you can do anything.
Framework.
Yeah, this is linear regression, in fact.
Yeah.
Oh, okay.
That's why
Okay, I didn't know that. Thank you so much.
Yeah, yeah.
The motivation is I write one piece of code and I want to work the same way on a single machine as like a huge cluster. So the nice thing is you can't do that with Scikit-Learn, like bare bones, like original Scikit-Learn, but you can do that if the algorithm is input in a TensorFlow framework. So.
One thing, and then on that note, we'll actually talk about what's called the estimator API within TensorFlow, which is kind of a second or third like generation attempt to with one model, right, like be able to actually run it locally on one laptop, one machine, and then also run it on a cluster. The sort of earlier styles of TensorFlow code, which is what you're going to see all the time, is the simple stuff is actually not very good at being distributed. There's code changes you have to make. There's like physical source code changes. Whereas, yeah, with the estimator API. And these TPUs actually have their own estimator API, which is very interesting, because TPUs do have kind of their own distribution model that's a bit different than typical like distributed TensorFlow. Like these TPUs like to be joined into what's called pods. You know, they're like
Kubernetes pods.
Yeah. And so, you know, and there's all kinds of like sharding strategies and things, and you would create your own like optimizer and your own estimator and then wrap it in the TPU estimator. I'll show you guys the code here in a sec, but yeah, and actually Scikit has that famous like flowchart diagram thing, right? Where if you have this much data, or if like this is your end goal, go to like clustering. If this is how much data you have, use k-means clustering, you know.
Yeah.
Pretty cool. Yeah. Yeah, whenever people like come up and say, oh, I'm like new to machine learning, I'm like, start here. So go a long way. One thing I want to point out on this slide is this is linear regression. And so you would write this in TensorFlow, and it would be a few lines of code. And when you train, this is the graph. So this is your graph set that you build up in your code. That's the graph that comes out of TensorFlow. And that's all the back propagation and all the safety checks and checking for exploding gradients, right? Yeah. So things like vanishing gradient, like that term. So these neural networks are making small little changes, right? They're like being trained, they calculate that there's an error in what they had estimated. Then they try to blame all the nodes that were part of that. And these numbers get really small. And because we're doing a lot of matrix multiplies, if you multiply a small number by another small number, it's eventually going to start to approach 0. You'll get to a point where you physically cannot represent with the number of bits that you're training, and it's going to go to 0. So there's like lots of safety checks. So I think this simple 5-node graph ends up being about 92 nodes. Now, that's why we have this post-training sort of optimization step, right? Like one of the things we do besides, well, the most obvious thing is just trimming it down and like getting it into a state where to get from my input, which is placeholder in TensorFlow terms, to my prediction is just the 5 nodes, right? Which is normal y equals like mx plus b kind of thing. Okay. If you don't do that, it's going to have to go through this entire flow, and yeah, there's going to be, it's like eventually going to get, it's not going to go through all of those, but it still has to make decisions to figure out, and if you can reduce the number of decisions being made on the that like prediction path, that's obviously optimal. One other thing, and this is our like area of specialty here, so I'm going to spend a second more on it, but I mentioned before about the float. So if you have 32 bits that you're allocating to each float that you're trying to learn, these weights or these parameters that you're trying to learn during the training process, that's actually quite a large value, right? That can be represented. If you want to, you could actually shrink it down to 16 bits. And now you can't capture as much of the nuances of the data set, but this is all hand wavy, like deep learning anyway. And the theory is there's a lot of data. And so, maybe we can actually get away. And the cool thing about dropping to 16-bit from the full 32-bit is that these processors, these GPUs, these CPUs can actually put 2 16 bits into one 32-bit core and actually do 2 calculations at once, right? They can kind of like pipeline 2. And if you go down to 8, you can do 4 at a time, because 8 times 4 is 32, right? So you will so you will like literally get a 2x speed up by going from 32-bit down to 16-bit. Now you'll lose a little bit of accuracy with your overall model because you're not capturing the full, you aren't giving the full 32-bit, but you can get through the training twice as fast, which is very important, especially when you're learning a new data set, or if you're trying to do the incremental training or the online training, you want to get through this as quickly as possible. And so what a lot of people do is they drop down to 16-bit, they sort of learn the intuition about the hyperparameters, and then in theory, they would go back to the 32-bit and do the full training for the full 2 weeks, but really they kind of stop at the 16-bit and they're like, you know what, it's 97%, I might get 98%. For this particular use case, 97 is good enough. And they only have to wait 1 week instead of 2. Yeah.
How much, I know I'm not saying this, but how much time do you spend processing your data?
Yeah, so feature engineering, and I assume this is on the training side, right? When you're training, yeah. So we personally, we stay as far away from that as we can. It's not always possible. One of our challenges, because we are focused on the prediction side, is oftentimes people find us because of that production focus. We show up and they're like, oh, by the way, we don't even have a trained TensorFlow model. And we're like, oh, okay, well, yeah, let's help you there. And so to clear the path for us to add value, we actually do have to help people with the training and the data ingestion, feature engineering. With that said, so one best practice with TensorFlow, and like pretty much with like every framework, you know, Spark would prefer this as well, is that you do all of the things in that framework. So in Spark's case, you would be writing Spark UDFs and making sure that all the operators can be understood by Spark. If you start straying and, you know, pulling in libraries from somewhere else, this happened all the time with Databricks. Like, and especially because we were trying to onboard customers as quickly as we could. People would say, oh, by the way, we forgot to tell you we have this custom Java, you know, UDF, this user-defined function that we run today, and we don't want to rewrite it in Spark. And we're like, oh, crap, yeah, here we go. And so essentially, these frameworks, both Spark and TensorFlow, separately, each, cannot do full optimizations until it can understand all the operations that are needed. And so one thing, because there's a tiny little hook that TensorFlow doesn't really tell you, but you could actually, I think it's called like _pyfunc or something, and you can give it any Python function and it'll run. It's the exact same downside as when you introduce a custom like UDF into Spark, where it can optimize and, you know, rearrange and do like logical to physical query planning and cost optimization until it gets to that custom code, and then it's just like, all right, yeah, we did our best. So the short thing there is you want to do as much as you can inside of TensorFlow. TensorFlow was very difficult up until recently to do simple joins and maps and filters and, you know, normal stuff you would expect with just like normal ETL. And so this is where you see TensorFlow trying to fight for the ETL market, and like Databricks and Spark trying to fight for the AI market. Yeah, like they're each trying to become the other one. So what's your guess? Which way would it go? Yeah, who would win in that battle? They were each charging. Google or Databricks? I won't use your name, yeah.
Lesser of the evil men.
Yeah, it's tough because Google's so big that the evil's spread out, and Databricks is so evil. But yeah, anyway. Yeah, I like ripping on those guys. This is, yeah, which by the way, they pretty much all unfriended me on. There was one day something I tweeted like really got to them, and then it was like unfriend all the founders of Databricks. So I was like, guys, I'm kind of joking. But, oh, because they said that nobody uses PMML. Yeah, that's what it was. It's what, predictive modeling markup language. Think of it like XML, like a way to represent.
Yeah, I've heard of that. We messed around with it.
Yeah, and yeah, everyone tries it out, right? It's not bad. You know, you can train a model in Scikit, export a PMML version of it, and then run that PMML version. I mean, all it's doing is capturing the weights and the, yeah, and then that goes into like an optimized runtime. And there's one that's JPMML, which has some weird licensing out of Estonia. It's not open source. And there's a lot of people using it kind of illegally. And then there was another company called Zementis. And actually, I was on an Apple project right after like Netflix. I was like pulled into a project, and yeah, they were using the Zementis commercial version. And Zementis just got bought by Software AG, I think. But they had a really optimized PMML, yes, I guess runtime, or yeah, like PMML engine, something like that. Yep.
You were ragging Spark's PMML, right?
And there was a webinar, because I watch all the Databricks like webinars just to see what's going on. And the one guy said, yeah, nobody, because someone, so, right, like Databricks doesn't like PMML because of that weird licensing thing that's like in Estonia, and because of the Zementis, there's no open source way to run like PMML. And of course, like Databricks either wants to own it, or they want like a suitable open source version, and then, you know, they can jam down people's throats. And so essentially Databricks is doing what a lot of people do sort of internally, which is write their own kind of markup language so that they can serve models. So like, yeah, basically PMML was a very early attempt to get a model into some like generic runtime that could then, you know, serve those, like take in like prediction or features and then make predictions. And so Databricks was saying on this webinar that, oh yeah, nobody uses PMML, you don't, because people, and yeah, people ask, like there were like 2 or 3 like webinars on this throughout the last few years, and each time someone would ask the live question of, well, do you support PMML? And they're like, finally the third one, the guy just slipped up and he was like, yeah, nobody uses PMML. Or, right, like none of our customers use PMML, and I tweeted something like, you must not have, you know, large customers or something. I don't know, it was something snarky like that, and that was enough. They had had enough of my shenanigans. So.
Good question.
Yeah.
I can't believe it. What does TensorFlow generate for the model and the pipeline?
And then
Still is Java, right?
So TensorFlow generates, it's now on its second version of what it generates, and it's actually become very specific now to model serving. So like I was showing before, there's I was going the other way. The simple, like that simple linear regression model. And actually I choose linear regression for this workshop on purpose because people don't realize that you can just do linear regression, and it's kind of one of those like eye-opening things, like, oh crap, I don't have to get bogged down in convolutions and get all confused and feel dumb. This is like what I normally would be using. Under normal circumstances, when you put that small little network, that small little graph into TensorFlow, it's going to create that huge graph. And when you just do a normal like checkpoint, you're going to save that complex graph, because checkpoints within TensorFlow are like that term is relative to model training. So you're checkpointing and saying, if my job fails, you know, that I'm 1 hour into my job, and if my job fails for whatever reason and I have to go back, I don't want to start over. I want to start from the last hour. Okay? And these like neural networks kind of naturally can be trained sort of right, like incrementally. And so the current that current checkpoint is from up until that point. It has the current weights that have been learned. You are then going to add more data, and like the assumption is that you are controlling the data going in. It's batch data. You've you know, did the like stratified sampling and made sure that the data is clean, and it, you know, and it's going to set up for success. When you go to serve, there's so like by default, it's going to shrink it down pretty well now. It like didn't used to, like before this new file format. It would literally just give you the checkpoint file, and it would be this nasty thing, and you would have to go in and do a lot of these post-training optimizations. They made it easier, and it's like literally called, was it save model format, and it will go in and see that big graph. So that's mutable, right? So all the weights in there are expected to change because it's a training job. When you go to actually serve the model, you're like quote unquote freezing that graph. You're going to trim all the other crap away. You're going to convert what would normally be a mutable variable into the non-mutable constant, right? The immutable constant. And there's huge performance gains when you can assume something isn't going to change, right? This is kind of a fundamental tenet of right, like computer science, right? When you know something won't change, you can, you know, do all kinds of tricks, and you could, you know, like threading ends up becoming like a non-issue, and you could, yeah. Yeah, exactly. Yeah.
So where do you get checkpoint?
Yeah, so keep in mind that training job, so when, yeah, like checkpointing in Spark Streaming land is like a bad thing, right? Performance has always been and there's all kinds of tricks and things you can do, and they all have drawbacks. Yeah. Yeah. And if you upgrade Spark, yeah.
Where do you checkpoint? I'm just asking.
So that's the thing, is that this is closer to an ETL job than it is.
Okay.
It's just it's a more complicated transformation. The T is a little bit more complicated than just a join or a filter. So the time to actually checkpoint here is right, like relative to a 2-week job. But you actually do need to pay attention to how often that you checkpoint. And one best practice that we'll hopefully get to in a slide here in a bit is when you are validating, so you're training, but you've also held out some validation data, right? Where you're going to take a checkpoint and pretend that that's the model that's going to go to production. That's the weights, that's what you've learned, and that's it. And typically, what you're doing is while you're training, you would kind of take a pause and go validate, kind of inline, and say, yeah, how is this doing? Because you don't want to continue training if you're starting to overfit, and if you're, if the validation doesn't hold up, right? The fear here is that you're like overfitting to a particular set of data. That's why you have to be careful what you choose to hold out to use for validations. It's all just kind of like general machine learning. But the one twist here is you don't want to hold up training to do that like validation step, right? So think of it like you would make the checkpoint, it would save it out to S3. You would then have S3 right, like notify something, and this is actually one feature of Pipeline, right? And that would then trigger and spin up a small little cluster to do the validation in parallel, and so training continues, right? So training, it's sort of optimistically continuing to train, spinning up, because you're typically holding out, 20% of the data, 15, like smaller. So the cluster size can be smaller, but the benefit is that if that validation takes an hour and you're training and validating, training, validating, you're sort of every other hour is you're actually allocating to train. So now you're doing it optimistically. Only if the validation like detects something strange would you actually then like notify somebody or have it automatically stop training. So that's kind of the like workflow, and we're using all the serverless function stuff within Pipeline to coordinate that. Yeah, so there's the predict method. Yeah, I showed that already. That's how you create 3 models. This is how you could do an actual load test locally. So I was mentioning this before, and yeah, the throughput's really low, 3 per second, 3 predictions per second, but it's on my local machine, and I can do it now. I can make a change. I could do another load test, and I don't have to like embarrass myself when I push out a model into production and it's performing really poorly. I could see it right on my laptop, that like relative to the previous version. We're gonna take a break here in a sec. Yeah, sit your ass down. Yeah, here we're doing some routing. So you can route. We have the word kube in here because we do have other implementations besides Kubernetes, but our most advanced right now is the Kubernetes version. When you route traffic, you can provide both a split traffic and a shadow. So I can actually show you guys a pretty cool demo. If you, maybe we can take a break after this, but if you go to community.pipeline.ai, if you wouldn't mind starring and getting $1,500 in our pocket from investors, that'd be nice.
Is that really a metric?
That was one VC. That was his opinion. It was the first time I'd ever heard anyone actually put a dollar amount. And then, yeah, the next step was 6,000 valued at 10 million. If you go to community.pipeline.ai, I don't know what happened there. There's a little box you could draw. You could do it on your phone too. You could draw a little number, hit predict, and we're actually going to shift the traffic here live. We could, let me show you. So here's traffic coming in. I'm going to put in a digit. See if it detects it. 0. Yeah, look at that, with 99% confidence. That's fun. It's telling you which variant served it up. You can click it again, generate some load there. Now, if we want to simulate, so let's say A is taking traffic, and we want B to shadow the traffic. meaning best effort. Send B as much of the traffic as you can, but don't hold up A. This is all asynchronous. It's fire and forget on to the shadow variant. Now I'm going to click this a bunch here, and I should only see, oh, I think someone's probably clicking it. I should only, yeah, it's not multi-tenant. Here, A is returning the value, but B should still be getting traffic. Let me see. I don't know. Might have gotten screwed up. I'm personally really bad with UI stuff, so never works. But B, so A is still the variant that's returning the prediction, but B is still getting traffic, right? And we can like compare system metrics, and at some point we don't have this wired up yet, but you can drill in and get like very, very detailed metrics. You can go to the business dashboards that show how the predictions actually are comparing based on a custom function that you've introduced to compare. This is 100% inspired by Algorithmia. I was like, I need that right away, and I just found some goofy way to do it. You can go here and actually, this should work. You can copy this curl, or you can grab the JavaScript, put it right into browser, you get the prediction. Okay. What's so funny, I was building this widget up here, and I was like, man, if I only had a, I was cobbling together the JavaScript, and I'm like, if I only had a way to copy and paste the JavaScript code. And I was like, wait a minute, I actually do. So I just went over here, clicked it, like literally grabbed it, put it in the HTML, and it worked. All right, so that's that. I think there might be one or two more slides, and then we'll take a break. And the food's going to be coming soon too. Oh, and so this is important, is most like training and all that, the data is collected and the accuracy is determined, and that's it. This is actually monitoring and tracking how the model is doing right? So this entire pipeline for each variant, the whole thing is shown, and we're constantly updating. So every 5 minutes, 15 minutes, we're actually calling back to what we call pipeline DB. And yes, pipeline DB is actually storing all this. And you can go in and then start to chart this. You can run Spark jobs on this data. You can basically do anything to like determine if a model is starting to degrade, right? Because of whatever changes in the business or different traffic patterns, that kind of stuff. There's this concept of like the efficiency score. I put a funny little trademark, even though it's not trademark. What's happening here? So we're tracking offline, and I just copied and pasted the numbers. That's what I was saying. But offline accuracy, online accuracy. So that's determined 24 hours later, 48 hours later, 2 weeks, 2 months later, whatever. This job, so it seems cheaper, which it is cheaper on the prediction side, but this job costs a shit ton on the training side because of GPUs. And now it's a smaller number of GPUs that are actually predicting, let's say. This is kind of a fabricated example. So it's not very efficient when this model first goes out because of the cost that was upfront. But as that model, because it's so much cheaper than the CPU version running the White Plains data center or whatever, that starts to go up, right? Like that efficiency score actually goes up over time because we're amortizing the cost of the offline training job. We're making it up on the. Oh, like how much would that have been? Well, if we do $6.50 an hour, how long are training jobs that you guys see?
Not that long.
Yeah. A day, yeah. So we could do 24.
I have another secret. Let's see if I can.
Yeah, $150. Yeah.
So if I can do almost all of it without GPUs, what is an overriding reason or when I would be using GPUs?
Yeah, we're actually dealing with this right now with a customer, because their intuition is that it's going to be faster with GPUs because offline their training jobs run a lot faster. And so keep in mind that when you're training, you're actually doing a prediction, right? That's the forward propagation through the network. And so by speeding up, right, and so it depends on if that GPU, so for the Tensor cores and the TPUs, those are really, really heavily optimized for forward propagation because it's almost always something times something plus something, right? And so that's why these GPUs, which are good at the back propagation, the training, can also benefit because of those tensor cores. It's going to speed up the forward propagation. So if you can make forward propagation faster, you can kind of make up for the slowness of the back propagation, right? So there's, and their like intuition, we're proving it out right now. Like, yeah, and there's really only one way to prove if the GPUs will be better on. Like typically training almost always based on the types of customers we see, it's a lot of image stuff and a lot of NLP and all that. But there's times actually we had one customer, they were using Keras, and Keras is a higher level sort of abstraction. It's its own API that you can plug in TensorFlow, plug in Theano, plug in CNTK, I think. Yeah, which is Microsoft's like TensorFlow. And they assumed TensorFlow was going to be the fastest, but they still wanted to use Keras just in case. And they actually, yeah, so like they were using Pipeline. It was a recurrent neural net. It was a pretty big payload too. It was one of the bigger payloads that they were trying to do on a web response kind of thing. They ended up shifting over to a stream, like doing it with streams instead. They realized that they didn't really need it real time like that. But the Theano model actually came out on top. Yeah, Theano plus GPU was actually the faster. And of course, they just end of life Theano, right?
Mm-hmm.
Yeah, no longer going to be extended, I guess. So yeah, multi-arm bandits ties into the traffic shifting feature, and yeah, this is pretty much straight out of Tensor Board these days. There's enough in there now. You don't really have to build your own. Slack. Oh, sorry. Slack is actually, we integrate with Slack. I'll show you guys here in a sec. So this is some of the traceability. You can see on a per prediction basis who was involved, traffic splitting, and also the sub models of the parts of the ensemble. This is a way to actually tap in and see the stream. So I was convinced that nobody would actually use this. So we're getting this request. How do I like deploy a model and I just want to see the inputs and the outputs. Like that's all. Like, yeah, why do I have to run a Spark job to see this? I just want to tap into it. And yeah, there's privacy, but we're like Americans, so yeah, privacy doesn't matter, right? But here you could actually visually, and this actually became one of the more popular things because, right, like no one's really had this on right when that model goes to production. Is it fraud? Is it just completely blowing up? And people wouldn't normally know this until either the business side calls or the customer support calls and come in, or they can see some other roll up that business has dropped some, and this is after the key metric has dropped. So here, like you can kind of visually see, and actually one customer, it's like retail, they have search terms coming in, and they have a pretty complex search result, search query. It's not just Lucene or whatever behind the scenes. There's a bunch of business rules. These search results now are becoming very complicated, and you have to bump up certain people who are paying, put them earlier, and if they're paying the same, how do you choose, and blah, blah, blah. So for like women's shoes or something, all they want to do is see, is model A the top 10 search results showing similar between the three models, or does one consistently not show, and it would literally be the images of the top 10. So you could visually see, and it's, you can dial it 5%, 1%, 0.001%. And of course, it's using Kafka behind the scenes and all that. Now, an extension of that, so back here I showed, this is MNIST, right? The demo I was just showing you, 0 through 9, the digit, you can see 2 is clearly the winner. It's a little bit different prediction for all three, but it's the same prediction, so that's good. How about, what's the worst case scenario here for the confidence? So here there's a clear winner, right? what would be, if you couldn't like determine, right, it would be 0.1. So each digit would be 0.1, 0.1, 0.1. It was, so it doesn't really know. So on the real-time prediction, it's still going to bring back, it's like usually 5 in that case. It just kind of picks like the median or whatever. So it's going to return something back to the user. That's fine. It's not a good prediction. We can actually set thresholds so that if it's not confidence above a certain threshold, pull that actual prediction off or somehow highlight it. And so like Kafka or something like that. So pull it off to Kafka in sort of like an unconfidence queue or topic. And now we actually have this set up to post to Slack. And we have a couple people doing this now where the data science